Hey there, this is Max, and we're going to be talking about overlapping chunks for this module. And luckily enough, it's exactly what it sounds like. We're going to overlap chunks by corrupting the size of it. Now, if you remember this slide from Module 1, this is exactly what I was thinking about when we were talking about why we were going so deep into data structures. For this, we're going to corrupt the size information of a chunk in order to overlap them with other chunks. And I think seeing this from the beginning, when you only knew what these data structures were, but you understand how they were useful for exploitation, I think it's good coming back to call those out later on. So the overview of this technique is we want to change the size of a chunk and force that to overlap the chunk with others. Practically speaking, here we have three chunks. Chunk 1, chunk 2, and chunk 3. And what if we change the size of one of these chunks to be over the top of the other ones? Well, now if we extend chunk 1 and it sits over the top of chunk 2 may still be in use. And so we get in this situation where we can use chunk 1 to corrupt chunk 2. So I know we've seen this data structure again, but it's always good to review stuff. The thing we really care about here is the chunk size. The size is the physical size of the chunk in memory that is allocated. And this is specified by the allocator, but depending on what the developer is asking for, it will also take that into consideration when it gives you that memory. The size also has metadata bits, the N, M, and P bits. The P stands for pre-bin use, as we talked about before. Chunks are byte aligned depending on the architecture, so 32-bit is 8 byte aligned, 64-bit is 16 byte aligned. Cool, so with that recap out of the way, we can actually get in the nitty-gritty details of how this technique works. So first, we obviously need to corrupt the size of the chunk. And this can be, and is most commonly going to be a buffer overflow, but there are situations where maybe use after free could be used if there's some consolidation that's happening. But you get the point. So depending on the bin we're actually going to do this in, it makes the difference for where we would actually want to do this at. So, did I skip a slide? I accidentally skipped this slide. That's okay. So there's actually multiple variations of this attack, and it really depends on the bin you're working in. The Tcache has no validations, of course, like every other Tcache technique. But there's also the fast bin and unsorted bin, and they just have more validations. What I mean is it will take the chunk that you're with and that it's working with, and it will look ahead to make sure that that chunk ahead of it is legit. So it'll take the size of the chunk, go ahead in memory based upon the size that's provided, and check to make sure that that is legit chunk size. You can work around these validations if you're clever, but it becomes hard in more complicated systems. There's also the shrinking to overlap technique, which deals with metadata bits not being updated correctly. There's a pretty cool post about it, and that is linked at the end of this, but we won't go through the technique. We will be going through Nmap though. So Nmap are very large chunks, and there are almost no validation on the Nmap chunks. And we're going to be doing a fairly fun module later on that goes through that technique. So with that in mind, we can go back to this. Depending on the bin, we actually need to corrupt the size at a different point. So for the Tcache, we're actually going to want to update the size before it gets freed. While with other chunks, or other bins like the unsorted bin, we would want to do it while it's free. At that point, we need to free the corrupted chunk if it's already been allocated. Finally, we need to allocate the chunk over that we've corrupted to overlap it with a different chunk. And this is a point in which we can start causing havoc. We have two things that overlap with each other. So visually speaking, we're going to start adding numbers to this to make this a little bit more realistic. We're going from purely visual to purely numbers over time. So here we can see we have two chunks of size hex 40 in size. Now we're going to change the size of hex 80 to be over the top of chunk 2. Sorry, we're going to change chunk 1 to be hex 80 and overlap with chunk 2. Words are hard. When we do this, we need to overlap, or the key thing is overlapping the size with the chunk in front of it. This can be a full chunk, in the middle of a chunk, kind of depends on what you have in mind. But the key concept here is we need two slots of memory to think that they own the same space. Similar with the concept of use after free. In the T-cache, it has no size validations, but there are some prereqs for this. First, the chunk size must be in the T-cache range, otherwise it won't go in the T-cache, and that's fairly obvious. The second thing is that the mmap bit cannot be set. If it's set, everything crashes and you don't want to deal with that. And you're probably wondering at this point, why do we need to reallocate? I've already corrupted the size. But the thing is, if we corrupt the size and then just let it be, the developer doesn't know this has changed. It's actually bad practice to look at the size of a chunk that you've allocated, because the malloc allocator should be completely agnostic to what your application. Different allocators are going to store chunk size information entirely differently, so it's unsafe to use that. So if the developer is not using this information, then the developer still thinks that it's hex 40 in size, and that's a problem, because we want to get it used as if it was hex 80. So we need to get it freed and then allocated once again. So we're going to free the chunk 1. And at this point, chunk 1 thinks it's hex 80 in size, and there's no size validations, so it goes directly into the hex 80 T-cache bin. And that's the cool part. So now if we allocate that chunk, after it's been in that bin, it will be on the request of a hex 80 chunk. So now the developer and the program thinks that it is hex 80 in size. And when we do a write to that chunk, we actually can corrupt the information within chunk 1, which is pretty awesome. So at this point, we can cause havoc and write to lots of different things. Now you can do lots of fun things with this. I think the obvious thing to do is use the overlapping chunk to corrupt the overlap chunk. And you can overwrite lots of important data. You can get information leaks, a lot of fun stuff to do here. But I also think it's important to consider the other direction as well. So using the memory corruption on the overlap chunk is pretty obvious. But what about the overlapped chunk corrupting the overlapping chunk? Remember, we have two different chunks to think they own the same space. If there is a write to chunk 2 after chunk 1 has been written to, chunk 1 can also be corrupted from the spot of chunk 2. I think that it's pretty easy to overlook this aspect of it, because chunk 1 is larger, but at the end of the day, if it's two sections are owned or believe they're owned by multiple things, you can cause major havoc with it. In order for this to work, you need to overwrite the size of a chunk. And even a single controlled buffer overflow with a single byte can work for this. You need decent control over allocation sizes and ordering. I think that's important. So this requires some heap feng shui. But the cool thing is this doesn't require any leaks to do. You just need to know where you're at relative to other chunks. The drawback, though, is this does need some heap feng shui, and you do need some good control of the allocation sizes. So that's the technique. It's not that complicated. There's not too much going on here. If we go back some slides and go back here, there's a couple of main steps. We need to corrupt the size. We need to make sure the chunk still works. So make sure the validations are passing. We need to free the chunk if it's one of those chunks that needs to be allocated while it's corrupted, like the T-cache. And then we need to, once it's freed, we need to allocate it to overlap with that other chunk. And at that point, we can cause havoc, which is the goal of all this. Thanks for watching. I'll see you in the next video.